Last meeting, we answered up to number 3. So today we'll just continue. Let's start number 4. At a temperature of 80 degrees Celsius, a steel tire 12 millimeters thick and 90 millimeters wide that is to be shrunk onto a locomotive driving wheel 2 meters in diameter just fits over the wheel, which is at a room temperature of 25 degrees Celsius. Determine the contact pressure between the tire and wheel after the assembly cools to 25 degrees Celsius. Neglect the deformation of the wheel caused by the pressure of the tire. Assume alpha is 11.7 micrometer per meter degree Celsius and E is 200 GPa. Okay, so to analyze, basically, we have a wheel, uh, a tire that is at a higher temperature than a wheel. Now your tire at 80 degrees just fits over the wheel. Okay, and then obviously, since your tire and wheel doesn't have the same temperature, it's gonna reach equilibrium to a final temperature of 25 degrees. Since there is a decrease in temperature, your tire will shrink. That shrinkage will cause pressure to your tire. And the question is, what is that pressure? Okay, so let's solve. Okay, first of all, let's write out our given. Initial temperature 80. And then thickness of your tire, 12 millimeters. Width of your tire, 90. Diameter of your tire is 2 meters. Usually when diameter is given, that's inner diameter. Okay. And then final temperature, it cools to 25 degrees Celsius. And then alpha, 11.7. Remember, converting micro to meter is just times 10 raised to 6, negative 6. Yeah. And then meter will cancel out. You're going to be left with just per degree Celsius. And then E, 200 GPa. Okay. So first, usually what we're doing is create your free body diagram and then create your equilibrium equations, right? Now, for this case, I'm going to start with its deformation. So, okay. So again, this is your tire originally at 80 degrees. Then afterwards, it cools down. Now remember, one of the steps in solving for things like this is to release the restraint. The restraint being this wheel. Okay? So if you release that, this is gonna shrink down this way. Okay? And so it could shrink this way, right? And this would be its deformation due to temperature change. And then the next step after that is to apply the force necessary to bring it back to its original position. So meaning this is also to bring it back, okay, you'll apply a force outward, right? And then this edge will go back here. So that means deformation due to temperature is equal to deformation due to applied force. Okay, so deformation due to force equals deformation due to temp. Force is PL over AE, and then this is alpha L change in P. L being its original length. The dimensions that this will move in is uh, circular. Okay, so if you want to take the length L, you can compute for its perimeter because that is the length in which the dimension of your object changes. Or since the original shape of your object is the same for force and for temperature, L just cancels out. Okay, so P area is okay. So now we need to get the area of our object. So remember, area is the cross-sectional area perpendicular to the direction of elongation, right? So usually, yes, we have a pipe, right? It's gonna elongate, then this is our cross-sectional area. Now what about this tire? So if we try to cut our tire, okay, we'll have something like this. Yan. Mm. Okay, so this is your tire. this is the perimeter. If you draw it fully, this is your tire. Cut it in half, you'll see that this is the cross-sectional area of your tire. So that is the area that we need. Okay, elongates this way or contracts. So the area of that would be, okay, this is your tire, thickness is given, this is 12. Okay, width of your tire is given, width is this, so it's also equal to this. And that is 90, right? A cross-sectional area is actually a rectangle. So area is easy to get, that's just 90 times 12, okay? So 90, they're already in millimeters, so no need to convert. Then E is 200, GPA, convert to MPA times 10 raised to 3. And then equate, alpha is 11.7 times 10 negative 6. Change in T, 25 minus 80. Now this will create a negative sign, right? But we're not we already know it's gonna shrink, right? So we're only concerned with the amount that it's deforming. So that means you can just write absolute value here. Okay? And then from this you can solve for P. Please solve. What's the answer? Correct. Rika, Diana, and Beatrice. Diana and Pascal. So it's 138,996. And our unit is Newton. Okay, now that's not what we're looking for. Recall, what are we looking for? We're looking for the pressure. So how do we get the pressure? So this figure should be a bit familiar to you guys because that's also the same figure we have for thin-walled cylinders. Then pressure is just this. This is your pressure, right? And then that pressure is being opposed by the forces within your cylinder. In this case, it's a tire. Okay. So these are the forces in your tire. Let's call that P. Since this P is also the force that creates your elongation or shrinking. So this P is the same as what we solved for you. Okay, because this is the force that is also perpendicular or axial to remember. And okay, so to make things clear, let's change the variable for this. Let's call this F. F due to pressure, P due to your deformation. Okay, and as you can see, we have another free body diagram. And then from that, we can write summation of forces equals 0. And you'll see that F equals 2P. And again, F is the force due to pressure. And how do we get that equation? That's pressure times area. Because pressure is force over area. Okay, so this is pressure. And area is this. And okay, so that's just P times diameter, or whatever this height is, and that height is the diameter, which is 2 meters. So this is 2 meters. So that's 2,000. Let's just write PA first. It equals twice, and then this P is just this, so we already know the value of that. So P times 2,000, and then this base, which is 90, equals to P. Pressure, small p for pressure. From this, please solve what's pressure. Correct. It's correct, Rika and Aaron. Yan yung Mendoza. Okay, 1.54. And then unit, since all of our units are in Newton and millimeter, so this is MPa. Okay, again, to differentiate, capital P is the force creating your deformation. Small p is pressure, okay? So that is number 4. Any questions for number 4, please answer in the chat. Okay, great. Since you don't have any questions, let's move on to number 5. A rigid horizontal bar of negligible mass is connected to 2 rods as shown in the figure. If the system is initially stress-free, calculate the temperature change that will cause a tensile stress of 90 MPa in the brass rod. Assume that both rods are subjected to the change in temperature. Okay, so again, to analyze, we want to know what change in temperature will cause a tensile stress of 90 MPa here. Okay, so first step, write out the other given. So stress in bar is given. Stress in bronze, and that is 90 MPa. So one of the first things to do is create your free body diagram and then equilibrium equations. Okay, let's call this A. Remember, rods, cables, etc. always are in tension. So therefore, this would be away from your member. Let's call this PBR for brass. And then here, again, away. So this is PCU for copper. And then this is 3 and 2. If we take summation of moment at A, we can create an equation relating PCU and PBR. Okay. So summation of moment at A equals 0. PCU, positive, clockwise, therefore positive. Perpendicular distance 3. PBR counter, so minus PBR times 5 equals 0. And then remember, another equation for P is stress times area. So stress CU times area CU times 3 minus stress BR area BR times 5 equals 0. Stress CU, we don't know yet. Area CU, we know it's 1,500 millimeters squared times 3 minus stress in bronze. It's supposed to be 90 MPa. So we're going to use that 90. And then area of bronze is 1,200. times 5. From this, we can solve what is stress in the copper. Correct, it's 120. Correct, Aaron and Elita Mendoza. Okay, it's 120. Now, why did I solve for this? What's the importance of this? I want to know change in temperature. Why am I getting stress? Because this will dictate how our system will move. Okay, so as you can see, stress in copper is 120 MPa. It's greater than stress in bronze. And then from this, we can solve for its actual deformation. Okay, so let's solve. Deformation of bronze muna tayo. Brass pala, not bronze, brass. Deformation of brass equals, remember we have an equation for that. It's stress over L E. Sorry, sigma L over E rather. Sigma of brass is 90. Total length of brass is 2 meters. Convert to millimeters. And then E is 100. Convert to MPa. What's the deformation? Correct. Correct, Aaron. 2 points ka na daw. So, Audrey and Trinity. Abaho ng region. So 1.8 millimeter. Next, let's compare that to the deformation of copper. So we've solved for this. It's 120. Length of copper is 3,000 millimeter. E is 120. Please compute what's the deformation. Correct. Beatriz and Julia Pascual Solomon. It's 3 millimeter. And as you can see, the deformation of copper is greater than the deformation of bronze. So how does that help us? Okay, so let's go back to the condition in the problem. It states there that it has to have a tensile stress of 90. Okay, so for tensile stress to happen, it needs to experience a tensile returning force. So what does that mean? So to explain, let's say you have a tube here, right? Okay. So if it elongate, if you this is the better example. Okay, right. So for this problem, you have your rod. Okay, it's stretched out to this point, and then it also shrunk to this point, and then in order for this to go back to its original position, it's gonna be stretched out again to this point. Okay, so this is your final returning force. Okay, the force that is needed to make it go back to its original position. It's in tension. Therefore, the stress being experienced by the system is also in tension. Okay, so that is what I mean. So going back to our problem, how will brass get a returning force? So there's two ways, I believe. That is one, there's only one way. That is for brass to deform so that it is needed to pull or stretch to go back to its original position. Okay? So that means if we have this brass, it needs to shrink this way so that we have a returning force moving it back to its original position. Okay? So that is the importance of that. And then the reason why we have this is to know how is it going to deform? What is now its final position? Since copper will deform more than bronze, that means this bar will move towards copper. Okay? Because this, again, copper deforms more than bronze. So the movement of this bar will depend on copper. We've already figured out that in order for brass to experience a tensile force, it needs to shrink first. Okay, so therefore, shrink. Okay, because if it elongates, right, your bar elongates, how will it experience another tensile force to put it back to its original position? No, the tensile force to put it back would be compression. Okay, so that's how we figured out that it's shrinking. And next, let's draw how it shrinks. Since copper shrinks more than brass, okay, this will move here. Okay. Okay. Again, the reason why I know this is gonna move here or bronze will move downward is because copper deforms more than brass. If brass deforms more than copper, this is how your bar will move. Right? So this is why we went through this equation. Okay. So now let's draw that. Okay. So this is what's happening. Okay. So your bar shrinks. Your brass will shrink to this final position. Therefore, this is the deformation due to temperature. Same way with copper, it will shrink to this final position. Therefore, this is the deformation due to temperature. Okay? And then the final, as I've said earlier, your bar will move this way. So this will be its final position. Okay? And then now we need to apply a force to move everything to this position. Okay? So that means from here, it's gonna be pushed to here. And this is now your applied force. Same thing here. This is the final position. It needs to be here. So we're gonna apply a force here. Okay. And then we've noticed we have similar triangles. And then whenever we have similar triangles, to get an equation, we use ratio and proportion. Okay, that's R&P, ratio and proportion. So let's see, considering this right triangle, right? To get this height, that's just deformation due to temperature minus deformation due to applied force. And then over base, which is 3, equals, now considering this entire right triangle, okay, so to get this height, that's deformation due to applied force minus the deformation due to temperature. And then total base is 5 meters. Okay, so let's just specify this is for copper. And then E. and then sigma P minus delta P minus delta T over 5 for brass. There. And then let's create our equations. Multiply everything by 15. Okay. So to simplify, so this becomes 5 times deformation due to temperature of copper is 3 millimeters. So that's alpha L change in T minus 3 of copper equals 3 times deformation of brass is 1.8. So 1.8 minus alpha L change in T. And sub in your values 5. Alpha of copper, again, it's micrometer. So multiply by 10 raised to negative 6. Length is 3000 millimeter. And change in T is what we're looking for. Okay? Yan. Wow. And then minus 3 equals 3. 1.8 minus alpha of brass, that's 18.7. And 1.8 minus 18.7 times 10 negative 6. Length is 2 meters, so 2000 millimeters. Change in T. Okay, and then from this, you can solve what's change in T. All right. Correct, Pauline and Vianney. Paragua, Vergara. 56.01 degrees Celsius. And then our answer is positive, therefore correct assumption. It is shrinking, therefore this is drop in temperature. Okay, and that is number 5. Any questions for number 5? Please answer in the chat. How about the others? Please answer as well. Do you have any questions? Okay, good. Let's move on to the last number, number 6. As shown in the figure, there is a gap between the aluminum bar and the rigid slab that is supported by 2 copper bars at 10 degrees Celsius, and your delta is 0.18 millimeters. So you have your rigid slab. There's a gap here of 0.18 millimeters. So this slab originally is being held up by your copper bars. Neglecting the mass of the slab, calculate the stress in each rod when the temperature in the assembly is increased to 95 degrees Celsius. And then for each copper bar, you have the following properties as well as for your aluminum. Okay, so to analyze, basically, originally, your system is at 10 degrees. Increasing it to 95, everything will expand, right? And then what we want to know now is the stress in each rod after that expansion. So let's solve. First, let's write out the given. Okay, let's start with copper. Area 500 millimeters squared. E is 120 GPa. And alpha is 16.8 micrometer per meter. Here's times 10 raised to negative 6. And then aluminum, area is 400 millimeters squared. E is 70 GPa. And then alpha, 23.1. Again, it's micro times 10 raised to negative 6. Okay. Now, first of all, the question here is, after they expand, will aluminum touch your slab? Okay, so let's check. So let's solve elongation due to temperature of your copper first. Alpha L change in T. 16.8 times 10 raised to negative 6. Length is 750. And change in T, final is 95, initial is 10. Let's include that here as well. Initial 10, final 95. So 95 minus 10. Please solve. What's the answer? Correct. Pauline and Trinity, Paraguay. So 1.071 to be exact. Right, and then do the same for stress due to temperature, deformation due to temperature of aluminum. Okay, so to get the length of your aluminum, that's 750 minus this gap. So 750 minus 0.18, 95 minus 10. Please solve. Correct. 1.47. Correct Elika and VMA. Wow, for that. Okay, so 1.47. And then comparing the elongation of aluminum is greater than that of copper. It exceeds the gap and exceeds the deformation of copper. So what does that mean? That means after reaching a temperature of 95, this is what's happening. Okay, gonna draw the free body diagram. So now your copper is pushing upward. Your aluminum is pushing upward because again, it has a greater elongation. Okay. So what happens is after elongating, so obviously this is gonna move as well, but aluminum expands greater. So eventually it's gonna touch the slab, and then it's gonna further elongate, raising up the slab. And then your copper is finished deforming due to temperature. while your aluminum is still expanding. So because of that, aluminum now is the one pushing up the slab. So let's call this PAL. Okay, and let's say this is how much your copper expanded. This should be the final position. So it needs to catch up. Okay, so meaning since copper is already beamed, or rather attached to the slab, since this is not enough, it creates a tension force downward. Okay, it's not supporting the slab anymore, it's pulling it downward because it doesn't deform enough. This is your PCU. And then from this, you can create equation, right? PAL minus twice PCU equals 0. And then we can call this your equation number 1. Next, equation number 2, we're gonna let everything deform. Okay, so let's have this slab. Okay, so this is the original, right? Then everything will expand, and it's gonna look this like this. Okay, so this edge will move somewhere here. Okay, and this is now the final position of your slab, right? And then if you remove that restraint, your aluminum bar will keep deforming here. Okay, so again, this is the final position of your slab after deforming. I'm gonna remove that restraint and let your bars move. Okay, your aluminum will elongate here. Okay, it's gonna elongate more than the final position of your slab because there's downward forces from copper not allowing it to move any more upward. Okay, so now this is the total deformation due to temperature of your aluminum. Next, copper. Copper doesn't deform enough, so it's gonna end up here. Okay, so this is deformation due to temperature of aluminum. This is deformation due to temperature of copper. Next, so now I need to bring it back to its original position, which is attached here, okay? Because that's the actual final position of your slab. So meaning I need an applied force pushing it downward here. So that's your sigma P for aluminum. And then I need an applied force pulling it upward here. So yeah, and that is your deformation due to applied force for copper. And then this is the gap before anything else happened, and that's your delta. Okay? And then from this drawing, we can create our compatibility equations. So I get the total length due to temperature of aluminum. Subtract these two. So minus sigma PAL minus delta. I'm gonna be left with this, right? And that is also equal to this, which is the summation of these two. So equals sigma T Cu plus sigma T Cu. Okay, I have that equation. Next step is just to write down the values. Okay, so this is sigma TAL. We already know that. It's 1.47. Use the stored value. Okay, 1.47 stored. Minus PL over AE. So PAL, length again is just 750 minus 0.18 for aluminum. Area of aluminum 400, E is 70. So 400 times 70 convert to MPa times 10 to 3 minus 0.18 equals PCU, and then this is 750. Area of copper 500, 120. So 500 times 120 times 10 raised to 3 plus sigma TC, delta TCU 1.07. Okay, and this is your equation number 2. Two equations, two unknowns. Please solve. What's PAL? Aluminum. Correct? Audrey and Michaela Santos and Manrique. It's 6699. Please solve. Don't just copy. 0.25. Okay. And then what's PCU? Force in copper. Okay, if you solve. Okay, very good. Jade, I'll give you 2 points because you actually solved for it. So it's 3349.63. And then the question is stress. So we already have the force in each rod. To get the stress, that's just P over A. And this is 6699.25 divided by 400. And you should get 16.75 MPa, and then stress in your copper, also P over A, and that's 6.70 MPa. And that is number 6. Any questions for number 6? Please answer in the chat. Okay, no questions. And that ends the topic for thermal stress. And that ends everything for module 2, every lecture for module 2. On Thursday, we're going to have a group activity. So same groupings as before. And then on Saturday, you'll have your modular exam number 2. Coverage is everything I've discussed in module 2. Okay? Any concerns or clarifications before I dismiss you? None? Okay, so by the way, I've realized some of you may have found where I get my questions from and are just copying the answers. I mean, that's fine. But please try to solve it first on your own if you get the same answer. Okay? Because sometimes the answers there are rounded off in the solution. That's why there's discrepancy in the final answer. Okay, so double check. For our class, it's always storing the values. There's no rounding off during the solution. Only round off for the final answer. Okay, so that's it. Midterm assessment. Okay, sure. Yeah, you can still submit. No problem. Any other concerns? None. Okay. Since you don't have any more questions, early dismissal, you may go. Goodbye, class.